So this is a problem using distributed load. So they want us to replace the loading by an equivalent resultant force and specify its location measured from point O. So the point O is on the left top of the beam. So what we need to do is we need to figure out what the resultant force is and how far away it is. So the sum, what's a pen? Sum of the forces in the y direction is going to equal that resultant force. And we'll just say up. Let's actually make it down as positive. Doesn't really matter, but there's all pointed down, so we'll make down as positive. So the sum of the forces in the y direction, so we have that 4 kilonewtons per meter that's distributed over 2 meters. And that's down, so do it positive. And then plus, and then the right side is that triangle. So it's 1/2. So we're basically trying to find the area underneath this. So we did the area here, which is just like a rectangle. So 2 meters times 4 kilonewtons per meter. And then plus, and then 1/2 of 6 kilonewtons per meter times 1.5 meters, just because that's a triangle. And that's going to equal our resultant force. So FR is going to equal 4 times 2, and the meters cross out. So that's 8 kilonewtons plus 1/2 times 6, which would be 3, times 1.5, which would be what, 4.5 kilonewtons. So that's also the meters cancel out. And then we just add those together, and we get the resultant force equals 12.5 kilonewtons. So that's part of the answer. And then they also wanted us to find the location from point O. So what we're going to do here is we're just going to sort of redraw these, or do the drawing again. So we've got, let's see, draw another beam. And we have that 8 kilonewtons per meter over 2 meters, and that's a rectangle. So it's just going to happen it's going to be in the middle of that. So at 1 meter is going to be that 8 kilonewtons, which is just 4 kilonewtons per meter times the 2 meters. And that's 1 meter in. And then the other one is that 1/2 times 6 times 1.5. So that was that 4.5 kilonewtons. So we'll put that here, 4.5 kilonewtons. And then for that distance, you remember that is just a third of the distance on the heavier side of it. So a third would be 0.5 meters. So it would be, so we have, let's see, this is 2 meters. This is basically where that triangle started. And then we're just going to go another 0.5 meters. So that makes sense. It's further from the center, it's closer to the side that has the higher force, higher distributed load. And so now we can just do moments to figure that out. So if we sum the moments about point O, that's going to equal that 8 kilonewtons. Or let's do our thing. Actually, I'm going to make it the opposite. I'm going to go into the board as being positive because they're all in that direction. So that's 8 kilonewtons times 1 meter plus 4.5 kilonewtons times 2.5 meters. And then we know that's going to equal that resultant force that we found times that distance. And that distance is what we're actually looking for. So we're trying to figure out where we can put that resultant force to represent all the forces. Maybe I'll draw it again here. So we're just trying to come up with one force, which we already found to be that 12.5 kilonewtons. And now we're just trying to find that distance here. So that gives us 8 kilonewton meters plus 4.5 times 2.5, 11.25 kilonewtons times meters. And that equals that 12.5 kilonewtons times that distance. And so that distance is going to equal 19.25 kilonewtons times meters. I just added those two together, and that's going to be divided by that 12.5 kilonewtons. So the kilonewtons cancel out. That gives us meters. So that distance equals, let's see, 19.25 divided by 12.5, 1.54 meters. So maybe go back and look. So they'd asked us to find the resultant force and location from O. So we found the resultant force and the location from O is at D.